Welcome to two projects. In this video, we are going to explain the project PDD Post Disaster Dataset for Human Detection and Performance Evaluation. Before diving into the execution, let me give you an overview of the project. So, post disaster human detection is all about using technology to find people in areas affected by disasters. When disasters happen, it can be really hard to locate and rescue survivors. So, this project aims to make that process easier and faster. So, instead of relying on people to search for survivors, we use technology to analyze images or videos of the disaster area. This saves time and reduces risks for rescuers. So, deep learning models are trained to recognize humans even in difficult conditions like low visibility or cluttered environments. This ensures that we can spot everyone who needs help. Finding people quickly means rescue teams can reach them faster, providing aid and getting them to safety sooner. So, this helps minimize the impact of the disaster and saves lives. By deploying this technology, we will be better equipped to respond to disasters and support affected communities. It is like giving them a better chance to recover and stay safe. So, deep learning models are trained on extensive datasets to recognize diverse human poses, sizes, and orientations, even in challenging conditions such as low light or obscured environments. Once trained, these models can be deployed on drones or unmanned aerial vehicles to survey disaster affected areas, providing real time information to rescue teams, therefore enhancing the efficiency and effectiveness of search and rescue operations. So, we will be building deep learning models in this project for human detection. Now, we'll look at the workflow. So, the dataset used for this project contains images and annotations depicting disaster affected areas. So, the first step in the workflow is reading the images. So, initially, the images from the dataset are read into the system for further processing. So, each image represents a snapshot of a disaster affected area, as I mentioned earlier. Once the images are loaded, various image processing techniques are applied to prepare them for analysis. This includes tasks such as converting the images to a format that the computer can understand, defining classes such as human and background, declaring bounding boxes around objects of interest such as humans, and converting the image data into a format suitable for further analysis. Normally, we will convert it into NumPy array. So, after this data pre-processing, we will apply data augmentation. So, to enhance the diversity of the dataset and improve the robustness of the models, data augmentation techniques are applied. These techniques involve making slight modifications to the images, such as rotating, flipping, or scaling them, to simulate different viewing conditions or variations in the appearance of humans in the scene. So, we will be training the models on original images but from different angles so that they can generalize well to different conditions. So, after the pre processing steps, the dataset is divided into two main parts: training data, which is used to teach the computer models, that is, deep learning models, how to recognize humans in disaster scenes, and testing data, which is used to evaluate how well the models perform on new or unseen images. After this, pre trained deep learning models such as variations of YOLO, that is, you only look once, DETR, that is, detection transformers, DINO, and FASTA RCNN are loaded into the system. So these models have been previously trained on large datasets and have learned to recognize objects, including humans, in images. So the loaded pre trained models are fine tuned or adapted to the specific task of post disaster human detection. using the training data from the dataset. So this involves adjusting the model's parameters and training it on the dataset to improve its performance on this particular task. Once the models are trained, they are evaluated using the testing data to assess their performance in accurately detecting humans in disaster scenes. So, this process helps identify which model variations perform best for post disaster human detection and provides insights into areas for further improvement or optimization. So, this is what we will be doing in this project. So, overall, the project focuses on creating advanced algorithms that can swiftly locate people in disaster zones. By doing so, rescue efforts become more efficient, increasing the likelihood of saving lives. Ultimately, the aim is to provide crucial support to emergency responders and those impacted by disasters. Now we look at the software and hardware requirements to execute this project. Hardware requirements are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Software requirements are application needed is Anaconda, primary language needed is Python, front-end framework required is Flask, back-end framework required is Jupyter Notebook, database needed is SQLite 3, and front-end technologies required are HTML, CSS, JavaScript, and Bootstrap 4. Now we look at the algorithms built. So in the base paper, author has proposed comparing all these models, and he has concluded that YOLO based models have outperformed other models. For improved performance, we are proposing YOLO V5X6 in this project. We will be building all these models and will compare the performance of all these models using different performance metrics like precision, recall, and MAP scores, and we'll select the best performing model for human detection from post disaster images. So after doing this, we have observed that YOLO model, YOLO V5X6, the proposed model, outperformed all other models. So we have deployed YOLO V5X6 into the Flask web application. So now we'll understand about the proposed model about YOLO V5X6 in brief. First, we'll understand about YOLO. So YOLO, that is You Only Look Once, is a computer vision object detection algorithm that quickly identifies objects in images by splitting the input image into a grid and simultaneously predicting bounding boxes and class probabilities. Unlike traditional methods, YOLO processes the image just once, making it extremely fast. It predicts multiple bounding boxes and their associated class probabilities for each grid cell and then removes redundant detections using non maximum suppression. So, this results in a final list of detected objects along with their bounding boxes and probabilities. So, we have different architectures in YOLO. So, YOLO V5X6 is one of them. So, YOLO V5X6 is a variant of the YOLO V5 object detection model designed to strike a balance between accuracy and speed. With around 2.4 million parameters, it offers good precision and recall while maintaining efficient processing speed. Its architecture is optimized to handle 1280 by 1280 input images, making it suitable for real time object detection tasks. So, YOLO V5X6 is chosen for this project due to its ability to provide accurate and fast detection, making it well suited for identifying persons in PDD images. Its medium sized architecture and optimized parameters allow for efficient processing of images while maintaining high detection accuracy, aligning perfectly with the project's objective of enhancing human detection capabilities in complex environments. So, this is about the YOLO V5X6 algorithm. Now, we'll look at the execution. Before executing the project, first we need to open the code folder which contains the project source code files. So this is the code folder and these are the contents I have in the code folder. So this is sample folder in which I have images on which will make the detections. This is static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. These are YOLO v5, YOLO v7, and YOLO v8 folders. I'm opening YOLO v5 folder. So these folders contain respective dataset for training that particular model. So in YOLO v5 folder, I have train and valid folders. I'm opening train folder. Here I have two subfolders, images and labels. So in images folder, I have required PDD images, that is post disaster scenes images. So I have 702 images with me. And in labels folder, I have annotation files for these images. We can say I have 702 annotation files. So each label file or annotation file corresponds to an image file in the images folder, providing details about the object's locations and classes within the image. So this annotation file corresponds to this image. Similarly, this annotation file corresponds to this image. In the same way, each annotation file corresponds to an image in the images folder. So these annotation files often follow YOLO format. So each line represents a detected object. So this is a line, this is another line. So we can see in this image, there are 9 objects detected. As we can see, we have 9 lines here. So each line represents a detected object. So we have 9 objects detected in the first image. So each line represents object's class index. The first column is the class index, followed by bounding box coordinates. So these are the bounding box coordinates normalized to the image dimensions. So this is X limit, this is Y limit, this is the width, and this is the height. So these are the bounding box coordinates, and the first column is the object's class index. In the same way, I have object's class index followed by its bounding box coordinates in other annotation files also. So each annotation file corresponds to an image in the images folder. So in second image, I have only one object detected. So on these images and on these label files or annotation files, we will be training the YOLO v5 model. So here I have valid folder also in which I have images and labels again. So on these images and labels in valid folder, we will be evaluating the model's performance. So train set is for training the models and validation set is for evaluating the model's performance. Similarly, I have train and validation folders in YOLO v7 and YOLO v8 folders also. And in those folders, I have images and label folders. So each folder contains the same images from all these folders. They have same images, but they are annotated differently. The annotation files will be changing because each YOLO version requires its own specific type of image annotations for training and testing the models effectively. So having separate folders like this helps keep the dataset organized and ensures that each YOLO version receives the correct annotations it needs to function properly. That is the reason we are having 3 separate folders here. So this is about the dataset, and this is app.py file. This .py file contains the information related to front-end logic. It includes coded in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. And these are model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the trained models. This is Notebook Jupyter source file which contains a combination of code, graphs, and outputs all in one place. So Jupyter Notebook allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. So it stores information like user signup details. So this is about the code folder. Now copy the path of the code folder from the address bar of the file explorer. This is the path. I'm copying it. Open Anaconda prompt. Use the command cd followed by a space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical error issues. After running the app.py file, the Flask framework will host the application locally at the default address, local host, and port unless configured differently. So this is the local host and this is the port. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I usually prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. And here we can see a sign up link, click on it. So if you are new users, we have to register ourselves first. Fill in these details and click on register button to sign up. And if we already have an account, we can directly log in by clicking on this link. So as I'm already a member, I'm clicking on this link. Here we have to give our credentials, username and password. I'm giving mine and click on login button. So it has redirected us to the detection page. So now we have to upload any post disaster scene image and the application will detect the humans from the image. Click on choose file button. So from sample images folder, these are the test cases I have. We'll try with the first image. Select the image, click on open. The image has been loaded. Now click on upload button. So we can see the application has detected humans in this post disaster scene. It has drawn bounding boxes around the detected humans. And we can see the label here. The application has detected and labeled them as persons. And beside the label, we can see a probability score telling us the confidence level of the application in labeling the detections as persons. Click on back, click on choose file. We'll try giving another image. We'll try with this image. We can see the application has detected a human from this post disaster scene. It has drawn a bounding box around the detected person. Here we can see the label, and beside the label, we can see the probability score telling us the confidence level, how confident the application is in labeling this detection as a person. Click on choose file. We'll try uploading this image. We can see the application has detected humans from this disaster, post disaster scene. Click on back, click on choose file. This time we'll try with this image. So we can see the application has detected all the persons from this post disaster image. We can see the bounding boxes drawn around each person detected. Similarly, we can upload any image from these test cases and can get the detections. We'll try with this one. We can see the application has detected the persons from this post disaster image. We can see the bounding boxes drawn around the detected persons. We can see the label and we can see the probability scores. We'll try with one more image. Click on choose file, select the image. We'll try with this image. Click on open. The image has been loaded. Now click on upload button. We can see in this post disaster image, one person has been detected. So in this way, we have to upload images from the test cases and get the detections of humans. So we can also execute the project using images downloaded from Google. We'll try that. So I'm searching for post disaster people images. So we'll try uploading images from here. We'll try with this image. Download the image. Click on choose file. Select the downloaded image and click on open. So it is saying only JPEG and JPG files are allowed. So the image format is not suitable. We'll try downloading another image. We'll try with this image. Select the image, click on open. The image has been loaded. Now click on upload button. So we can see the application has detected the persons in this post disaster scene. It has drawn bounding boxes around the detected persons. Click on back. We'll try uploading another image. We'll try with this image. Click on choose file. Select the downloaded image and click on open. The image has been loaded. Now click on upload button. We can see the application has detected all the persons in the image. And we can see the probability scores telling us the confidence level of the application in labeling them as persons. Click on back. We'll try giving some more images. We'll try with this image. Select the image, download it. Click on choose file. Select the downloaded image, click on open. The image has been loaded. Now click on upload button. We can see the application has detected all the persons in the image. We can see there are many people here. Click on back. We'll try uploading this image. Select the downloaded image, click on open. Image has been loaded. Now click on upload button. So we can see the application has detected these people. We can see the bounding boxes drawn around the detected people and we can see the probability scores. Click on back. We'll try with one more image. We'll try uploading this image. So this is the image. Select the image, click on open, click on upload. We can see the application has detected the humans in the image. In this post disaster image, it has drawn bounding boxes around the detected persons. It has labeled them as persons, and beside the label we can see the probability scores telling us the confidence level of the system in labeling them as persons. So in this way we can also take images from Google and we can make the detections. Now click on graphs link here. So here we can view all the visualizations made. So this is precision and recall graph of YOLO. This is F1 score graph. This is confusion matrix graph. This is precision scores comparison graph, a horizontal bar graph comparing precision scores. So in this graph, on x-axis I have precision scores and on y-axis I have algorithm names. So these are all the algorithms built. Similarly, this is recall scores comparison graph and this is MAP scores comparison graph. So we can see YOLO V5X6, the proposed model, has outperformed all other models in MAP comparison graph. We can see that here. And it is also doing well in precision and recall. So these are all the graphs plotted. Now click on sign out link. So the project's development of deep learning models for post-disaster human detection enhances rescue operations efficiency, saving lives. By optimizing model performance and supporting emergency responders, it significantly contributes to disaster management efforts, aiding communities in times of crisis.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.